Hello students, today we'll discuss about the isomerism in the coordination chemistry. This is the third part on the series of lecture where I am discussing the coordination chemistry. In the first lecture, Werner's theory was discussed and then the IPAC nomenclature was discussed. So here isomerism we are going to discuss, and then in the next video we are going to discuss crystal field theory. So let us start. Before starting going to isomerism, just get some knowledge on the ligands, different types of ligands associated with the coordination complexes. So ligands can be many type, and it can be divided in monodentate ligand, bidentate ligand, polydentate ligand. Sometimes they are called chelating ligands and ambidentate ligands. So what are the differences in between these ligands? Now ligand is what? It should have pair of electrons which it can donate to the metal atom and make coordinate bond with the metal. Okay, right? So when a ligand have only one donor atom, it's a water having oxygen only having lone pairs of electrons. Hydrogen don't have, right? So only oxygen can bind with the metal center. That's why it will be called as monodentate ligand, because it is only one donor center. Okay, that's why mono. Mono is one. Similarly, ammonia, cyanide, chloride, pyridine, these will work as monodentate ligands. And bidentate ligands, what? Bi means two. When a ligand will have two donor centers. Here you see in ethylene diamine, there are two amine centers where two nitrogens are there which can donate electron pairs to the metal. Okay, therefore it will be called as bidentate ligand. Similarly, acetyl acetonate, oxalate, those are also bidentate ligands. And which are polydentate ligands? More than two. If donor atoms are there, like in this diethylene triamine, there are three centers where it can donate to the metal atom and can make bonds. Those will be called as an EDTA, another example, a very common ligand. Okay, so those are called polydentate ligands. Now, what are chelating ligands? So, bidentate or polydentate ligands, when they both are donating to the metal and making a ring, that time this will be called as chelate, and the ligand will be called as chelating ligand, because the bidentate or polydentate ligand, it made bond with one donor atom or both. Okay, when it is making bond using both of its donor atoms, then a cycle will form, a ring will form. That's why then it will be only called as chelate. So similarly, some other examples are also given, you can see here. So then these are chelating ligands, right? Ambidentate ligand is what? When a small ligand having two donor atoms, here is Cn minus. So sulfur also having lone pair of electron, nitrogen also having. So there are two donor sites, but they cannot act as bidentate ligand because both at the same time cannot donate to the metal center. Either one sulfur can donate or nitrogen can donate to the metal. Both cannot make a bond with the metal at a time, because then it will be a three-membered ring, okay, which will be a very strange ring. That's why it is not possible. So it will be called as then ambidentate ligand. Okay, two, it can donate, it can make bond either through S or through N. Similarly, NO or CO is also called ambidentate ligand. I hope you understood the different types of ligands in the coordination compounds. Here, the list of, because ligand can be negatively charged, positively charged or neutral. So, list of many ligands are given which are negatively charged or positively or neutral. Okay, so these are the different types of ligands. Another thing you should know that what is homoleptic and heteroleptic complex. So this is a complex where if all the ligands are same, then it will be called as homoleptic complex. So these are the two examples of homoleptic complex, and this is heteroleptic. Why? Because all ligands are not same. Then it will be called as heteroleptic complexes. Now let us move to isomerism in coordination compounds. So isomers are what? You already know that if two or more compounds, those are having same chemical formula. Okay, chemical formula will be same, but different arrangement of atoms. Then they will be called isomer of each other. Here in the coordination compounds, isomerisms, we will divide it in two types. First, stereoisomerism and structural isomerism. Again, inside stereoisomerism, there will get geometrical isomerism and optical isomerism. Inside structural isomerism, we'll get linkage isomerism, ionization isomerism, coordination isomerism, solvate or hydrate isomerism, ligand isomerism, and two more types of isomerisms we'll get. We'll learn one by one. Let us discuss first the structural isomerisms. So structural isomerisms are what? Isomers are what? If they will contain same number of atom, okay, right? Those they will have same number of atom each kind, but differ in which atoms are bonded to one another, and are called structural isomers, which differ in structure or bond type. So structurally they will be different. How? Okay, so let us see with examples. So one first type in this structural isomerism is ionization isomerism. What is this? So we understand this through these examples. Okay, here the structure of two coordination complexes are given, where you can see their formulas are same. It is having cobalt as a central metal atom, 5 ammonia ligands, 1 chloride ligand, 1 bromide ligand. Here also it is same. But where it is different, you can see the chloride is inside the square bracket and bromide is outside here. But in this case, bromide is inside, chloride is outside the coordination sphere. Okay, so these two are changed in the bond is different. Cobalt is having direct bond with the chloride, but here cobalt is having ionic interaction with the chloride here. So this is the difference in the bond formation between metal ligand bond. Okay, therefore these two will be called as ionization isomerism. Now, why the name is ionization isomerism? Because already we have discussed before in the Werner's theory that these ligands which are inside the coordination entity, these are not ionizable. They are having covalent coordinate bond with the metal atom. So these are not breakable in water. But which are outside the coordination sphere, they are having ionic interaction with the metal center. So when we dissolve in water, we get these ions separately, but will not get the chloride ions or ammonia separately. That's why, but when we dissolve this complex in water, then we'll get chloride ion, not bromide ion. But in this case, we'll get bromide ion, but not chloride ion when we'll do the test for bromide or chloride. This will give the positive test for bromide, and this will give the positive test for chloride, not for bromide. Okay, because this is inside, it will not break. I hope you understood now. So as we are getting different ions by dissolving it in water, that's why the name is like that. It is ionization isomerism. I hope you understood here. So it is given here. You can see this complex when it is dissolved. So chloride, and here we are getting bromide. Right? Okay. So let us move to the next type of isomerism, which is called solvate isomerism. So these a very similar type of isomerism results from replacement of a coordinated group by a solvent molecule, which in the case of water is called hydrate isomerism. Okay, So let us understand this solvate isomerism with example. This is one example of a coordination complex where outside chloride is there and also two water ligand is there. It is having bright green color. Now you see the second one example. Here you can see in the first one two chloride ligands was inside, but in the second one chloride is gone outside and one water molecule came inside. In the first one there was four water molecule. In the second one chloride is replaced with one water molecule, right? And the color also changed. In the third one, another chloride is replaced by another water molecule. Means another water from outside it went to inside and another chloride came outside. And this color also changed to violet color. So all these three will be called as solvate isomers. Okay, and as in this case, the solvent is water. It can be other solvent also. In this case, the solvent, water is a solvent, you know. So as it is water, we can also call it hydrate isomerism. Okay. So that means replacement, here it is written, replacement of a coordinated group by a solvent molecule. So here we are replacing chloride ligand with a solvent molecule, that is water. Okay, that's why all these three will be called as solvate or hydrate isomers. I hope you understood this isomerism also. Let us move to next one, that is coordination isomerism. So in this case, the anion and cation complexes of a coordination compound exchange one or more ligands. Okay, let us understand again with an example. So you see, this is an example of a coordination compound where both cation is also a coordination compound, anion is also a coordination compound. Right. Now, if the ligands are exchanged in these two coordinations here, if or the other way, the metal may also exchange. You see, copper goes here, zinc comes here. Copper come here, zinc came here. So the ligand with the associated metal changed. Okay, here zinc was associated with the amine, but here zinc associated with chloride. Okay, so the metals changed the position, or other way we can tell that ligands also changed the position. Okay, then these two will be called as coordination isomers. Okay, another more examples are given here. Okay, so we are exchanging the ligands between two coordinations here, but it as a whole it is a one compound. Okay, so this is called coordination isomerism. What is next one? It is linkage isomerism. So to show a coordination complex, a linkage isomerism, it should have an ambidentate ligand bound with it. So we already understood a few slides before that what is ambidentate ligand. So ambidentate ligand will have two types of donor atom, like HCN minus NCS. So where H can also donate, N can also donate, or nitrate, NO2 minus or ONO. Okay, so we can see with the example. See, this is nitro, and when it is donating from nitrogen atom to the metal, then it will be called as nitro. But when oxygen will donate, because oxygen also having lone pair of electron, it can also donate to the metal, then it will be called nitrito. So this complex which is having a NO2 ligand, so I have given the structure also. In this complex, see, once the NO2, the nitrogen is coordinating with the metal. Another case, the oxygen is coordinating with the metal center. So these two will be called as linkage isomerism. Why linkage? Because this link between the metal and the ligand atom, that is different link, right? The link is different with the metal and the ligand. Okay, so that's why it is called linkage isomerism, and linkage isomerism will be only observed with the ambidentate ligands. Okay, so let us move to next one, which is called ligand isomerism. So in this isomerism, the ligands show isomerism. How? You see, this is a ligand which is 1,2-diaminopropane, and this is 1,3-diaminopropane. Now their formula is same, so they are isomers. Okay, now this is in short, it is called as PN, this is TN. Okay, so when this is making a complex with cobalt and other formula is also same, it is making a complex with the cobalt and other formula is also same. So as a whole, this one and this one, the formula is same, but isomerism is shown where? In the ligand system. Okay, that's why these two will be called as ligand isomers. Okay, let us move to next one, that is coordination position isomerism. So in this type of isomerism is shown by those complex compounds which contain bridging ligands and arises when the non-bridging ligands are differently placed around the central metal atom. What does it mean? You see this example and this example. So coordination position isomerism will occur when only bridging ligands are present and non-bridging ligands are also present. But the isomerism will be shown due to the position changed by the non-bridging ligands. You see here, this side, this cobalt is having 4 ammonia. This cobalt is having 2 ammonia and 2 chlorides. But in this one chloride will shift to here, one ammonia will shift to here. So this side one chloride will come, ammonia will be 3, one chloride will be here and 3 ammonia. Okay, now both side is equal. So as the non-bridging ligands are differently placed in these two compounds, so these two compounds will be called as coordination position isomers. And the last one is polymerization isomerism. So in this type of isomers, okay, you can say that one is looks like monomer, another looks like the polymer of the monomer. So these two will be called as polymerization isomers. In this case, we have one platinum, 2 ammonia and 2 chloride ligands. And here 2 platinum, 4 ammonia, 4 chloride ligand. So if you just make if this is a monomer, so if it is doubled, we'll get like as looks like polymer of this one from the formula. Okay, so these two will be called as polymerization isomerism, and these two also similarly. Okay, now we'll move to stereoisomerism, right? So what is stereoisomerism? When stereoisomerism occurs, so in case of compounds which is having same chemical bonds but have different spatial arrangements, those are known as stereoisomers. Okay, that means the bond with the metal and ligand, that will be also same, because the previous case we have seen the bond between metal and ligand, it may be different. Some are inside directly bonded with the metal, some are outside the coordination sphere. That changes may happen in case of structural isomerism. But in stereoisomerism, here the bonds will be same, but all the molecules are three-dimensional molecules, right? It is distributed in the space. So the arrangement in the space, that will be different. The ligand arrangement in the space, if that is different, then those will be called as stereoisomers. Okay, and this is further can be divided into optical isomerism and geometrical isomerism, right? So first, let us discuss about the geometrical isomerism. The metal complexes that differ only in which ligands are adjacent to one another, means cis position. See the example of these two. So these two same type of ligands, B and B, they are adjacent to each other, means the BMB bond, that is less than 180 degree. Then they will be called as cis position. or if they are directly across from one another, then it will be called in transposition. This one. So this is square planar complexes. These two B are just exactly opposite to each other. Their bond angle is what? BMB, that is 180 degree. So these two will be called as geometrical isomers. One is cis, one is trans. Okay, so the coordination compounds with coordination number mainly 4 and 6 exhibits this type of geometrical isomerism. And this type of isomerism is only can be obtained in heteroleptic complexes. We have already discussed that what is homoleptic and what is heteroleptic complex. To get a geometrical isomerism, the complex should be heteroleptic. Why? Because you see here, this complex is a homoleptic complex because all ligands are same. Now, if all ligands are same, then what is the problem? These ligands cannot be identified from each other because all are same. Now, one ammonia is cis to another ammonia because this is octahedral complex. Octahedral complex having 90-degree angle between each other, right? So this that is less than 180 degree. That means this ammonia and this ammonia are cis in position, and this ammonia is trans position than each other. So then how we can tell this complex as a whole, cis or trans? How we can differentiate? We cannot tell it cis, we cannot tell it also trans with a confident. Okay, that means if we cannot differentiate between cis and trans, that means it is not showing actually any geometrical isomerism. So that's why any homoleptic complex will not show geometrical isomerism. Similarly, this is a tetrahedral compound which is homoleptic. Because of homoleptic it will not show. Even if it is not homoleptic, it become a heteroleptic complex. In that case also, the tetrahedral complexes don't show any geometrical isomerism. Why? In this case, the reason is two ligands. The structure is such that the two ligands, they cannot be exactly opposite to each other. Why? Because to become opposite to each other, the angle should be 180 degree, like this one, which we have discussed. But in tetrahedral shape, we know the angle between all the ligands and metal, that will be 109.5 degree. That is the ideal angle in the tetrahedral structure, right? So there is no position of 180 degree. All are less than 180 degree angle. That means all ligands are cis to each other. So they can always stay in cis position. They can never have a trans position, trans isomer. That's why actually it is geometrical isomerism will be not applicable. That's why to tetrahedral complexes. Okay, so I hope you understood these points. Now in square planar complexes, it shows the geometrical isomers, okay, because cis and transposition is possible. But if I take a complex like Ma3B, where M stands for metal, A3 is one kind of ligand, A, and another different kind of ligand, that is B. So this is the complex. In this case, will it show any geometrical isomerism? This will not show. Why? Because you see, these three are identical ligands. Now A is cis to this A, also trans to A. So we cannot tell it is cis or trans. Again, B is also cis to this A, B is trans to this A. So we cannot tell this is cis or trans. When there is a confusion, we cannot tell if it is cis or trans. That means it is actually not showing any geometrical isomerism. Okay, so wherever we put the B, it will be same complex. Okay, there is no isomers. If the formula is Ma2B2, means 2 A type of ligand, 2 B types of ligand. This example already we have just seen that in these cases, cis and trans is possible. When the same kind of ligand are cis position, okay, adjacent, then it is cis. When they are just opposite to each other, then it is trans. Okay. So here are some more examples of this Ma2B2 we understood. Now if Ma2BC is another third kind of ligand, if it comes, then again it shows cis and trans. Then what we'll do, the same kind of ligand, if it is adjacent to each other, then it will be called as cis. If they are trans to each other, then it will be trans. So in this case, we'll just see the same ligand positions. If bidentate ligand is there with two different atoms, donor atoms, like this one, so in this case, cis and trans is again possible. When this donor site and this donor site is same, so they are in the cis position, so then the complex will be called cis. But when this donor site and the same donor site, they are opposite in the position, then it will be called as trans. Similarly, M, A, B, C, D, when all four ligands are different, they will also show geometrical isomerism. Okay. So in this case, one atom, one donor site will keep constant, and with that we'll keep other ligands cis or trans positions, and then we'll get these three kind of isomers possible. Okay, so this will be called as also geometrical isomers to each other, but here three kinds of possibilities there. If square planar complex contain the bidentate ligand but both the donor sites are same, then there is no possibility again of showing any cis or trans. So only one isomer is possible when both donor sites are same. But if donor sites are different, then it can be cis or trans. Now let us discuss about in octahedral complexes what and how we see this geometrical isomerism. So if we take MA5B type of compound where M is metal, 5 A types of ligand and 1 B type ligand. So this is the structure. This is the structure, right? So in this case, cis trans is possible. So again, in this case also, it is not possible because again, it is confused that if same ligands are there, they are cis also and trans also to each other. So only one type of structure possible for this kind of complexes. If AMA4B2 type of is there, then cis trans is possible because two same ligands are there. Now we can compare their position according in respect to their position. We can tell cis or trans. In respect to A, we cannot tell. Okay, because they are also cis, they are also trans. But at least in respect of B, we can tell it is cis or trans. With these two, if they are in like this, they are cis. This is cis, but this is trans. This is trans. Okay, that means as in respect, at least in respect of one ligand, we can define it cis and trans. Then we will tell it that it will show the geometrical isomerism cis or trans. Now for MA3B3 type of complex, where three same type of ligand, another three same type of ligand, it will show geometrical isomerism. Yes, but it is called not cis or trans, but it is called facial or meridional isomerism. What is that? If three same kind of ligand is placed in one face of the octahedron is having 8 faces, right? So if these three, you see just in one phase of this is octahedron structure. So one phase of the octahedron is occupied by these three ligand. So this will be called facial isomer. And if this tree is put in such a way so that it is not making a face, but it is going through the octahedron structure like this, going through, right? So this will be called as meridional isomers. Okay, right? Next, what? So this is one example what different kinds of geometrical isomers is possible when this kind of is there. You can do it as your homework. And then let us move to optical isomerism. So what is optical isomerism? So optical isomers have the unique property of rotating light. What? So if a complex solution is kept in a polarimeter, solution here, and a plane polarized light. This is plane polarized light. This is light where it is going every direction. When it is passing through a polarizer, then it will be in only one directional light. So when it is passing through the sample solution will be here, and then you see the direction changed. It was going in this direction, now it changed to this direction. That means the compound rotated the direction of the light. So if a compound rotates a plane polarized light, that means this compound is optically active. Okay, so that is the experimentally we understand that a compound is optically active or not. But if we have the structure of the compound, okay, then how we can say it is optically active or not? So two methods are there. One is to find out the mirror image. If the mirror image of the compound is not superimposable, which is first one, then they will be called they will be optically active. And another method is plane of symmetry method, where if the compound have plane of symmetry, then that will be optically inactive, and if there is no plane of symmetry, then optically um, inactive. Okay, no plane of symmetry means active. So this is the easy way to find out if optically active compound is there or not, by finding out the plane of symmetry is passing through the molecule or not. Okay, so in this complex FeCl3F3, here this is actually the plane of symmetry. It is going through this compound. Okay, this is a facial isomer. Okay, this is a facial isomer. Okay, so if it is going through it and then it is having a plane of symmetry, that means it is optically inactive. Okay, now some compounds are given here where bidentate ligands are coordinated with the metal center, and this type of octahedral complex is forming, and the mirror image is like this. So this mirror image actually non-superimposable to this one. If we take this one and try to put on this one, so it will be non-superimposable. Okay, so if so, that means this is also a optically active compound. Here some more examples are given. You can try with by placing a plane of symmetry. If it is present, so that compound will be optically inactive, like this one. This is having plane of symmetry in this plane. So that means it is optically inactive. This is also inactive. This is also inactive. Okay, but it is having plane of symmetry. But this, the cis compound, this is bidentate, this compound, this is the cis in respect to Cn. So this is optically active because there is no plane of symmetry present here. And now some octahedral other complexes example is also given here. You can try it in your home. Okay, by this one we finish the isomerism of coordination complexes.